Hey everybody, welcome to section 5.1 of stats. And this is unfortunately the way we're going to have to do this for a little while. Let me turn this off, see if it helps. Yeah, it did. So let's turn that off too. So we're going to have to do this over the computer, which is probably nobody's favorite, at least of all mine, but we can do it and it's going to work. So what we're going to do today is we're going to start talking about random variables. And my goal is not just to show you the notes and read them to you, but I do need some sort of structure. So that's kind of what I'm going to go with. So what I'm going to do is I'm going to share the screen here. And I want to pull up this slideshow. All right, and you'll see this is what we're going to be talking about today. This section introduces the concept of a random variable and probability distribution. And then if you skip down here, back up. We're going to show how to find the important parameters like mean and standard deviation. And that's where we're going. And then we're going to determine whether outcomes are significant. And we've talked about this before with significantly high and significantly low. And that's what we're going with here. All right, so let's start off with talking about what a random variable is. A random variable, usually we're going to use X, has a single numerical value for each outcome of a procedure. So let me kind of put this in one way we'll use random variables. Let's say we were going to have some sort of experiment where, let's say we were going to flip a coin twice, and then we were going to record how many heads there were. So our random variable might be the number of heads we get when we flip a coin twice. All right, so that means it could be 0 because you might not get any heads. The value of a random variable could also be 1 because you could get 1 head, or it could be 2 because you could get 2 heads. In that example, the random variable would be 0, 1, or 2. Now, there are a couple of different types of random variables. And the first one is just what I was talking about just then. That's the discrete random variable. And it says it right here. Discrete has a collection that is finite or countable. Now, finite just means it's not infinite. Countable, it can be infinite, but we could count them. The best example I can think of is like the counting numbers. You can count 1, 2, 3, 4, 5, 6, 7. You can continue doing that forever. So it is infinite, but you're counting them. What you can't do is like, and I think in terms of numbers always, but you can't count all the numbers between 0 and 1 because you've got 0.1, 0.001, 0.0001, and so on and so on. So no matter how you want to break it up, you can't count them all. There's just too many. It's infinite. All right. A continuous random variable is infinite. And the way I like to think about it is like instead of taking the number 0 or 1, it could take 0 or 1 or any of the stuff in the middle. It could be anywhere in the middle. So a lot of times when we're measuring things, that's going to be a continuous value. And we've talked a little bit about continuous and discrete before. But in this case, that's what we're meaning. When in terms of random variables, a good example might be if we were to look at, let's see, I have it written down here somewhere. All right, and so now, sorry, it takes me just a little while to get used to this. Yeah, right here. If we're talking about a discrete random variable, you'll see it right up here at the top. Discrete, the values of the variable are finite or countable. An example of that would be the number of shots you take before you make a free throw. Okay, you're going to shoot, and maybe it takes you 2, maybe it takes you none, maybe it takes you 23. Maybe you shoot forever and you're terrible and you never make one, but you can still count how many shots are taken. That would be discrete. All right, continuous random variable, there's an infinite number of values and you can't count them. And like I said, most measurements are going to be continuous. And an example of a continuous random variable would be how long it takes you to make that free throw. You know, it could be 20 seconds. It could be 21 seconds. It could be 21.000 seconds. It could be 21.0037004 seconds. You get the idea. There's just an infinitely small difference between the choices, and we can't list them all. Those would be continuous. All right, so that's a random variable. Random variable is like how many times something happens, basically, in our first few examples. Now, the next thing is going to be a probability distribution. And the probability distribution, it tells you the probability for each value of the random variable. All right, now, this is if we have a discrete random variable, we can do this in terms of a table. We can draw a graph usually pretty easily, sometimes a formula. Continuous random variables, we usually have to have some kind of formula. So most of what we're going to be dealing with today, in fact, pretty much all of what we're going to be dealing with today is going to be discrete random variables. So looking here, we have this example we talked about earlier. We have a coin, and that coin is flipped 2 times. Well, we can get 0 heads. That's one possible outcome. We can get 1 head. That's another possible outcome. Or we can get 2 heads. That is a third possible outcome. The only values our random variable can take are 0, 1, or 2. Now, if you look, the probability of getting 0 heads is 0.25 right there. The probability of getting 1 head, that's 0.5. And the probability of 2 heads is 0.25. And this is what's called a probability distribution. All right, and we're going to be dealing with these. We're going to be, and usually the ones we're going to be dealing with are going to be in the form of a table, because most of the things we're going to be calculating today, especially, are going to be discrete, and a table is probably the best way to do that. So let's see, let's pick up here. All right. Now, there's some characteristics of a probability distribution that you have to have. The first one is there a numerical random variable and its number values are associated with probabilities. In other words, what we just had, we had a random variable that could take 0, 1, or 2. It wasn't head or no head or tail. That wasn't the value. The value was 0, 1, or 2. Okay, that's important. All right, number 2, the sum of P of X has to be 1. Now that's all the probabilities. So in fact, I think it's in here somewhere. All right, here's the chart again. Same chart we had a while ago. These are our probabilities over here. And if we add those up, we get 1. That's a requirement in a probability distribution. Now, if you look here, sums like 0.999 or 1.001, those are there may be times when you're doing a problem, although you probably won't, but there may be times when you try to add up all the probabilities and you get something that's very close to 1, like these two things, 0.999, 1.001, and we're going to go ahead and say, that's basically 1. Somewhere in the rounding off of the probabilities, we got just a little bit of error in there, but it's not enough to worry about. All right, and then the third thing, and that is that the probability has to be 1. A probability of any event has to be between 0 and 1, and that's true. I mean, we know that probability has to be between 0 and 1, and that's what we said when we first started talking about probabilities. All right. So that was the first basic idea. We have random variables now that we kind of know there's continuous and there's discrete. And we've also talked about a probability distribution. And we know that when you have a probability distribution, all the probabilities have to be between 0 and 1. And if we add them all up, we should get 1 or something very, very, very close to it. So now let's pick up here. It's being slow. All right, now just a side point. When we're talking about probability distributions, we are talking about the entire population. We're not talking about a sample. So instead of having a parameter, instead of having a statistic, we're going to have parameters. Parameters go with population, statistics with sample, P with P, S with S. And when we're talking about probability distributions and doing things with those, there are two major parameters that we're worried about, and they're the mean and the standard deviation. Now, the mean is we're going to represent by the Greek letter mu, and you see it right there. It's like a U with a little tail on the front of it. And it's defined here the theoretical mean for infinitely many trials. Now, I don't like that definition because it uses mean to define mean. So basically, we can think of it as the average results we would get. You know, it's the expected value. That's another thing, that another definition for mean is expected value. And yeah, it's the expected value. It's what we would expect to get. So in that earlier case, if we do flip a coin twice, how many heads do we expect to get? That's what the mean is. That's the average outcome. It's what we would expect to get. Now, when we're talking about discrete random variables, which we are here, we can directly calculate the mean. All right. And the mean is this value right here, mu equals. Now that thing right there, that big E looking thing, that is called sigma. And sigma means we're adding things up. It's a summation. So we're taking the value of the random variable times the mean, times the probability. Then we're doing that for the next one. The value of the random variable times the probability. And then we're going to add all those up, and that will give us our mean. All right, so let's let's do this another way. Let's pull the PowerPoint back up. Come on, there we go. All right, here we go. Like I just said, here's your mean. All right, if we wanted to calculate that mean, all right, here's our chart we were using a minute ago. 0 has 0.25, one head is 0.50, and then the probability of two heads is 0.25. All right, so to find the mean, this is the one we're looking at right here. So this is the mean. See how they're doing that? You have 0 and 0 times 0.25 is 0. 1 times 0.50 is 0.5. 2 times 0.25 gives us 0.5. And when we add all those up, we get 1. So that mean value of this probability distribution then is going to be 1. And remember earlier we talked about that's what it means. That's what we'd expect to get. Now you and I have talked before about the probability of a head being 0.5. So if we flipped a coin twice, we're kind of expecting to get one head. That's what the mean is, and that's how the expected value idea works. Now, we also want to find the standard deviation. Okay, and the standard deviation is sigma. Okay, that's the other thing we want to find. But what we're normally going to find is sigma squared and then take the square root. You know, because sigma is equal to the square root of sigma squared. And if we're doing this manually, we're usually going to use this second one here. Sigma squared equals sigma squared equals the sum of x squared times p of x. And then we're going to add all those together, and then we're going to subtract mu squared. So really, it's kind of like this. We put these in parentheses. We find this first, then we subtract mu squared. All right. So now, here we go. So look here. 0 squared, this is our x, 0 squared minus the mean. Okay, I said we are going to use the other one. Actually, in this case, we're using this formula, but it's fine. All right, so 0 minus the mean squared times 0.25 is 0.25. 1 minus the mean squared times 0.5 is 0. 2 minus the mean squared times 0.25, and that's our probability, remember, is 0.25. And when we add those up, we get 50. If we were to have used the other formula, we would have gotten the same thing. So this means that sigma squared equals 0.50. Sigma is the square root of sigma squared, which is the square root of 0.50. And just kind of consulting down here where I have this worked out, that's 0.7. All right, let me erase a little bit of that. All right. So that's our answer. Sigma is 0.7. All right, and see, there they have it. Right there, they've kind of given us that at the end. All right, so that's how we find the mean and the standard deviation. So let's look at another example. I think I've got a couple here. Yeah, I've got a couple. And then let's look at that and see what this would look like. There we go. Sure. All right. This is stuff we've already done. All right, so here we go. Groups of 5 males are checked for color blindness. Now, here's what this means. They went out and got a group of 5 men, and they checked them to see if they were colorblind. Then they went out and got another group of 5 men and checked them. Then they went out and got another group of 5 men and checked them. All right, and then, so our random variables here, X, that is the number of people in that group that were colorblind. Okay, so X equals 0. There could be 0 people, could be 1, 2, 3, 4, or 5. Couldn't be more than 5 because there's only 5 people in the group. And then over here, in each case, we have the probabilities associated with each of those numbers. The probability of having none of your 5 people be colorblind is 0.662. Okay. Now, one thing I do want to show here, look at this last number, 0.000. And we learned in the last unit that a probability of 0 means it's never going to happen. It's impossible. That's not what this means here. This would be a number that's very, very, very small. And when we round it to 3 decimal places, it would be something, it would be this, it would be 0.000. So maybe this number down here is 0.000000004. And when we round it, this is what we get. So it's not exactly 0, but it, that's what it rounds to. All right, so going back to the problem, we're determining if this is a probability distribution. And if it is, we want to find the mean and standard deviation. Okay. Now, when it comes to talking about, is this a probability distribution, there were 3 properties, if you remember. The first one is your random variable had to only take number values. And if we look over here under this X column, sure enough, all of those are just numbers. All of our probabilities had to be between 0 and 1. All of these are, this one's 0, but that's fine. It's 0 to 1. It's not outside of that range. And the third thing is that all of the probabilities have to add to 1. So if you look, this column right here, the P of X, come down to the bottom of the page, or bottom of the screen, I did that. I added these up, 0.662 plus 0.283 plus 0.51 plus 0.003 plus 0.001 plus 0.000 equals 1. So yes, it comes out. This is, in fact, a probability distribution. So it makes sense to talk about its mean and its standard deviation. So now we're going to find its mean. And I really wish, you know what, I'm going to try. No, I can't do that, I bet. Can I make it smaller? Will it let me do that? That's not going to let me do it right now. That's fine. All right, we just may have to flip back and forth. All right, so now this is perfect. I want to find the mean. So remember, to find the mean, what I'm going to do, and up here at the top, I'm going to take the value of the random variable times its probability. So 0 times 0.662. And if you look down at the bottom, that's the first pair. 1 times 0.283. There you go, down at the bottom. 2 times 0.051. Here we are. 3 times 0.003. 4 times 0.001. 5 times 0.000. All right. And I did this in my calculator. I added all those up. And when I did that, I did the multiplications, I added, and I got 0.4. And that is my mean. So that means in a group of 5 men, I'm really not expecting to find one that's, colorblind. 0.4 of a person. However you do 0.4 of a person. I don't know. But that's what it relates to. All right, so we found the mean. Finding the mean is pretty simple. It's a little obnoxious because we have to type in all those values, but we can do it. All right, now in this problem, I used that second formula for the standard or for the variation, where I take the random variable squared times its probability. I add all those up, and then I subtract the mean squared. Okay. So for instance, 0 squared times 0.662, all right, plus 1 squared times 0.283. And remember, these come from that chart earlier. Okay, if I were to, all right, 0 squared times 0.662, 1 squared times 0.283, 2 squared times 0.051. All right. 3 squared times 0.003, 4 squared times 0.001, 5 squared times 0.000. I added all those up, and then I subtracted 0.4 squared because that was my mean. It's the sum of all these minus the mean squared, and we get that sigma squared equals 0.37. But don't forget, we don't want sigma squared. We want sigma, all right? So we have to come down here and we just plug this in the calculator. Sigma is the square root of whatever sigma squared was, so we get 0.6. And that's a common mistake, especially on homework, because you do all of this stuff up here, all of this addition and multiplication, and you think you're done, you just forget to take that next step. That happens. But, we're going to get past it. All right. So that's that example. We determined it was a probability distribution, and after that, we were able to find its mean and standard deviation. Now, let's look at the next example. Groups of 3 children are being checked for being underweight. In other words, we've got these groups of 3. So in a group of 3, how many could be underweight? You could have 0, you could have 1, you could have 2, or you could have 3. That's our random that's our random variables over here. Now, associated with 0 is the probability of 0.001. Associated with 1 is a probability of 0.008. Associated with 2 is this probability. And remember, the first thing we want to ask is this a probability distribution? And in this case, it's not. So here's why. Because if we take these 4 values right there, I'm sorry, let's run it up a little bit. No, that's it. So it's 4. Take those 4 and we add them up. That's 0.91. This equals 0.1. Not 1. 1 is what we wanted it to be. All right. We wanted it to be 1, but it's not. It's 0.01, which means this is not a probability distribution. and we're going to go on and about our lives. We're not going to worry with it anymore. All right. Oh, let me erase that. All right. Okay. And you see it right here. It's written. The sum of the probabilities is not 1. Therefore, this is not a probability distribution. So far, we've talked about a couple of things, really. We've talked about random variables, and we've talked about probability distributions. Then we've talked about the mean and standard deviation of those. And everything we've done so far has been a what we call a discrete probability distribution. We'll get to continuous later, but we're going to have to do those a different way. But for right now, we just need to get the idea of how things work, what the mean is and what standard deviation is with these discrete ones, because they're a little easier to understand. All right. Now, back in, I believe it was the first unit, we talked about values that were significantly high or significantly low. In other words, these would be things that are just way out there. They're pretty far away from our normal data. And we had this rule of thumb that if we were 2 standard deviations away from the mean, above it, 2 standard deviations above, anything above that is going to be significantly high. If this is our mean and then we go down 2 standard deviations, anything down here is significantly low. And as it happens, that exact thing still is true. Come on now. There we go. All right, and you'll see it right there. In earlier sections, we talked about if you're significantly high or low, it's 2 more away. So very simple example, and this is something we did almost exactly like this before. An experiment is conducted in which a coin is flipped 10 times and the number of heads is counted. All right. The mean of those mean number is 5. That's our mean. And they tell us the standard deviation is 1.7. And we're asked to find if 1 head in 10 flips is significantly low. In other words, we're going to start at the mean. We're going to go down 2 standard deviations. Actually, that may be going to the right. Anyway, whatever way it looks for you. It looks like it's going to the left for me. So we're going to start at the mean. We're going to go 2 standard deviations down from that. And we're going to find out what that number is. And if the number, what number were we asked? 1. If 1 is below that, yes, it's significantly low. And okay, here's the math. Exactly what I said. The mean minus 2 standard deviations. That's this right here. So 5 minus 2 times 1.7. They told us what the mean was. It was 5. And the standard deviation is 1.7. And when we do that little calculation, we get 1.6. So yeah, any number of heads lower than 1.6 is significantly low. All right, 1 is less than 6. So getting 1 head in 10 flips would be significantly low. That's not anything new. We've done that before. We've done almost that exact problem. But that's not the only way we can do it. And in fact, the way I'm about to show you is a way we'll do it later. And it actually is one we use more often. All right. So what we can do is rather than calculating the mean and the standard deviation and then finding what 2 standard deviations above and below is, we can use probability. And here's the deal. A certain number of successes is significantly high if the probability of that number of successes or more is less than 0.05. Okay? A number of successes is significantly low if the probability of that number or fewer is less than 0.05. So in both cases, that probability is going to be less than 0.05. So let's look at an example that see how that works. All right, groups of 8 births are studied. So there are 8 babies. And then the number of girl births is recorded. So out of 8 babies, how many were girls? All right, and we know that that's a discrete random variable. There are 8 births. So how many girl births could there be? There could be 0. There could be 1. There could be 2, 3, 4, 5, or 6, or 7, or even 8. So there's, those are the values that our random variable can take. And then over here, you'll see over here on the left, they give us a probability distribution table. And I'll scroll it up in a minute because we don't get the whole thing. It goes up to 8, but I need to read it. All right, we're asked to find if at part A is 1 girl birth significantly low, and if 6 girl births is significantly high. So let's look at part A, right here, part A. And we're going to use this right here. I want to know if it's significantly low. So I'm going to use the second part up here. I want to know if the probability of 1 or fewer is less than 0.05. Okay, 1 or fewer. That'd be either 1 or 0. That's the two options we had. So if you look right here, that's what I did. Oh, I'm sorry, that looks bad. I wasn't picking my nose, I was scratching it. I should probably edit that out. I hope I remember that. Anyway, down here on the bottom, probability of 1 or fewer, that's going to be the probability of 0 plus the probability of 1. Now, how do I find those? Well, I'm just looking over in the table. The probability of 0 is 0.03. The probability of 1 is 0.14. And when I add those together, I get 0.17. Sorry, 0.017. That is less than 0.05. Therefore, yes, the probability of 1 girl birth is significantly low. Since this probability is less than 0.05, it's significantly low. All right, the next question is whether 6 girl births is significantly high. So again, it's significantly high if the probability of 6 or more is less than 0.05. What is 6 or more? That would be 6 girls or 7 girls or 8 girls, because we only went as high as 8. So the probability of 6 plus probability of 7 plus probability of 8, right there. All right, it comes directly from over here. 6 is 0.104, 0.014, 0.003. And we add those up, we get 0.121. So that means that's a lot bigger. That's much larger than 0.05. So yeah, 6 girl births is not significantly high because the probability is not smaller than 0.05. Okay, that's what I wanted. That's what we didn't get. So that's significantly high, significantly low. The last thing I want to talk about is this thing called the rare event rule. Now, the rare event rule is kind of just like, it basically is something that tells us either our assumptions faults or our data's faults. So here's the idea. If we've done the numbers and we have found that a certain event it's basically impossible. The probability is 0.00000000001. And then we actually observe that happening. Then there's two things that could have happened. We could have actually seen that once in a lifetime event. Or there was something wrong with our original assumption, okay, that the probability was really small. So I have an example here, of course. All right, suppose we make the assumption that 99% of students in a class will pass. All right, 99 people, we're assuming that 99% are going to pass. Now, therefore, the probability of anyone failing is very, very low. Okay, in fact, the probability would be 1 out of 100%. 1 out of 100 people would fail. That's 0.01. That's a small probability. The probability of 9 people failing under this assumption that 99% would pass is very, very small. Because if you look down here, I actually calculated it, and you could have calculated this too. The probability of 9 failures is 0.01 to the 9th power, and look at this long number, 0.000000000000000000001. I think I got lost in there. But that's a very, very, very small number. So if there were a class where we had made this assumption that 99% would pass and 9 people failed, then probably our assumption was wrong, that 99% of people would pass. That's what the rare event rule is. That if there is something by our assumption, by our original proposition, something that should be very, very, very unlikely and almost never happen, and then it actually does happen in real life, we need to go back and look at our original assumptions. All right. So that's the rare event rule. Now, I meant to have a timer going, but I don't have a timer going. I'm guessing we're about 30 minutes or so. That's as long as I really want these to be. Remember that there will be a question and answer session at our normal class time, should be every day. So that's what time? I have a schedule over here. That is 11 o'clock Monday, Wednesday, Friday. So 11 o'clock Monday, Wednesday, Friday, I will do a Zoom session. And what I want to do during that time is to ask questions, answer questions. I think the video lecture is, although maybe not ideal, I would rather spend my time with you answering your questions than in presenting the material that I just did. And if you don't have any questions, you don't have to come to that Zoom session, but it's there for you if you need it. So this is the end of this section, and I hope you have a good day.